Right, this is a review of the first section of Chapter 6 on thermal chemistry. As you see here, thermal chemistry is the study of energy and heat associated with chemical reactions and or physical transformations. Throughout this chapter, we're going to actually look at two different things. The study of the energy and heat, right here, associated with the chemical reactions and or physical transformations. So we're going to look at how the energy and the heat play along with chemical reactions, and somewhere inside this chapter, we're also going to look at some physical transformations. It's not going to be towards the end, but what we're talking about is a solid to going to a liquid or a liquid going to a gas, and what kind of heat is involved with that, whether it's exothermic or endothermic or something like that. And I'm going to get into all these words here in just a moment. Okay, energy is the ability to do work. That's a physics definition. It's the ability to get something done. Also, according to the first law of thermodynamics, which we're going to get into in the next couple slides, that energy is the ability of being conserved. You can't get rid of energy. You can't destroy it. You can only change its forms to something else. I often say, like for example, if you're charging your cell phone, where do these energies come from? It comes from the heat from the coal, and the heat from the coal boils a big pot of water at this is by the way, this is all at a power plant. We have coal burning power plants in Ohio. So we light up the coal on fire. The coal produces a bunch of heat. Now that's thermal energy. Boils water. Now the water is now a little kinetic energy, and the water is boiling, so it produces a steam. So we have a lot of kinetic energy. This causes a turbine to turn. Now that is a mechanical energy, and that causes the turbine to turn, which moves electrons. Now we have electrical energy. The electrical energy travels down the wire to your house, and while you're plugging in your cell phone to charge up your cell phone, is creating a chemical potential energy. So you have all these different energies that are being converted, and these energies can be not only is it they're lost, or actually it's kind of leached out, but it's not destroyed. Okay, so you can have energy, it's always conserved, you can't destroy it or you can't create it. Energy could be heat, right here, or energy could be work. So since both heat and work, it could be either, they're both measured in what are called joules. Okay, these could be joules, which is a unit of energy, or it could be kilojoules. Energy is also a state function, which means that you're not concerned with how you arrived at someplace, only that you're there. So in other words, the path and how to get to someplace is completely irrelevant. For example, if we were going from here to California, some of us walked, some of us flew and had 3 layovers, some of us took a train. So it doesn't matter how you get there, only it matters that in a matter of a couple days or something like that, however long it takes to get to California, we're all there. Okay, so it's completely irrelevant of how you got there, only the fact that you're there. That's what a state function is. We took a look at state functions when we talked about Pivnert. Okay, next, when we're talking about these things, and again, this is an introduction to this chapter, we need to separate the universe into two aspects. The first aspect is going to be the system. Now, the system is I don't know, the little tiny environment or the big environment that you're considering, and the surroundings. Now, as far as this chapter goes, as far as this textbook goes, as far as anything that we take a look at, the system is the part that you are concerned with. So we want to see how work is done on the system. We want to see if energy is leaving the system. We want to see if work is being done by the system, on the surroundings, those kinds of things. Okay? The last couple things that I want to talk about as far as an introduction goes is exothermic and endothermic reactions. Exothermic reactions release energy to the surroundings. In other words, the surroundings are going, since it's releasing heat to the surroundings should get a little bit hotter. And endothermic reactions are opposite. If this one was released and then this one is absorbed, then the surroundings should get a little bit cooler. Okay? Next. Energy loss and energy gain. All right. Um, the energy gained by the surroundings must equal the energy lost by a system. Here's the thing. If you have energy of the surroundings, so let's say the energy of a system, and the energy of the system loses energy, that is equal to the energy gained by the surroundings. So energy lost by one is the energy gained by the other. Okay? So the next point right here says if this energy is released by the system, where did all this energy come from? This energy comes from potential energies located in bonds. Located in bonds. So what we have is some molecules that are loaded with energy. Now, we're going to talk about this a little bit more when we talk about making bonds and breaking bonds. But if I want to break some bonds, I need to put energy in. So if I put energy in to break bonds, then all of a sudden I have all these atoms floating around in different places. And when the bonds come back together, they release energy. So where does this energy come from that's released? It comes from making bonds. Okay? So this whole bonding concept, destroying bonds or breaking bonds, means I have to put energy in. And if I'm going to take energy, if I'm going to make bonds, I take energy out. Okay? Energy in is endothermic. Energy out is exothermic. Okay, here is an exothermic reaction. You'll notice that the energy level of my reactants is quite high, and then it goes through this downhill process where the products have less energy. So you notice the difference between these two here is considerable in this case. You'll notice whatever energy here I have here is lost as heat. Okay, so an exothermic process will expel heat to its environment, and the environment tends to get, or the surroundings tend to get hotter because the system expelled energy from it to its surroundings. The next diagram I have is an endothermic reaction. You notice I have something different. I have reactants that are lower in energy and products that are higher in energy. So how do I go from something that's low to something that's high? Well, if you take a ball and you're standing down here and you have a ball or you have a brick or something like that, and you want to get the ball up here at the top of the hill, you have to put your own energy in to carry the ball up the hill to get to here, or at least get to here. Okay? So in order to get reactants lower in energy to products that are higher in energy, I have to put heat in to do this. That's an endothermic reaction. Now, exothermic reactions by far are way more common than endothermic reactions. Okay? Endothermic reactions are not tough to do, but they are a little bit more on the rare side than as compared to how common exothermic reactions are. Okay, thermodynamics, we took a look at this already. It's a study of heat, the energy in its conversions, excuse me. We already took a look at the law of thermodynamics that's saying that the energy is neither lost or gained, it's only converted. You can't create or destroy energy. What I want to take a look at is this whole concept right here, saying that internal energy right here is equal to Q, which is the heat, plus the work. Okay, so any internal energy of any system can be found by adding together the heat and the work. Now, since heat and work are being added together, they both must have the same units, in this case, joules. Okay, in most cases, joules. All right, so thermodynamic quantities are such. Now, again, an introduction to what we have here. We have two things. I have a sign and I have a quantity. Well, the quantity could be anything, 88, 188, 2088, it doesn't matter. But the sign is what I really want you to pay attention to here. If I have a negative sign, the negative sign says energy is going out of the system, or the energy of the system is decreasing. Okay? If this is the case, if I have a negative symbol, it means that energy is being expelled, or exothermic, or exiting, or leaving the system. If this was a positive up here, rather than a negative, then I have this particular case where energy is going now into the system from the surroundings. Or remember, it's going in, or endothermic, or entering, or going in. Want to say it again. It all has to do with the direction. So the plus or the minus does not necessarily, isn't what we're normally used to as far as being plus or minuses. It has to do with whether energy is exiting or leaving the system, or it could be work that's either exiting or leaving the system. Now let's take a look at sample exercise 6.1. And this is on page 233 in your textbook. It says calculate the delta E for a system undergoing an endothermic process in which 15.6 kilojoules of heat flows and where 1.4 kilojoules of work is done on the system. Okay, So it says calculate the internal energy, and that's Q plus W. All right. Now, the thing that you have to pay attention to is calculate the delta E for the system undergoing an endothermic process. So I have 15.6 kilojoules of heat, but is that plus or minus? Well, it tells us it's endothermic. Endothermic means plus, or heat is going into the system. And, oops, I don't know that one yet, although it will be plus, and you'll see why that's in a second. And it says heat flows where 1.4 kilojoules of work is being done on a system. So I have 1.4 kilojoules of work being done on a system. If work is being done on the system, we have to ask ourselves, is work going into the system or work coming out of the system? The answer is that work is going into the system. So therefore, that must be plus as well, and our answer is 17.0 kilojoules. Okay? Next, work and gases. Okay, as far as work and gases go, we have work either being done by a gas or work being done on a gas. The first thing I want to do is talk about work being done by a gas. The equation that we're going to plug into when doing these calculations is right here. Work is equal to negative pressure times the change in volume. By the way, delta stands for change in. Change in, okay? In other words, final minus initial. It always has to be final conditions minus initial conditions. So that's delta V, or change in volume. All right, so what we have, if we have work being done by a gas, it means gas is going to be pushing on its surroundings. So the system is going to be doing work here. Work will be leaving the system to push on the surroundings. Therefore, I have expansion of the gases. So work is leaving, so I'm going to have a negative symbol. And you'll notice if the gas is expanding, it's getting bigger. It's getting more in volume. So therefore, I have a positive delta V. You'll notice something here, that the negative and the positive are opposite in signs. And if you take a look at this statement down here, the signs of work and delta V have to be opposite. So if you're a little confused on whether the work is going to be negative or positive, just think, if the gas is expanding, it's growing. It'll be positive, so work's got to be negative. In this case down here, if gas is being compressed, we're going to have the gas being squished. That's going to be negative, and so therefore the work will be positive. Okay? So if work is being done on a gas, it means the surroundings are doing work on the system. So therefore work is going into the system, so therefore I have my positive symbol right here. Okay? So this is a little bit confusing. So as we go on in the chapter and as we work out some of these details of whether work is being done on a system or by the system, we'll get a little bit more practice on how to deal with that. Okay, this is a slide. You guys can take a look at this on your own. Heat is being given off as negative, heat absorbed as positive. Go ahead and take a look at this. You can pause the video here to write this stuff down or to contemplate it. I'm going to keep moving. What I want to do is go to sample exercise 6.2. Sample exercise 6.2 is on page 234 of chapter 6. And what this says is that the question says calculate the work associated with the expansion of a gas from 46 liters to 64 liters at a constant external pressure of 15 atmospheres. Okay, so it says calculate the work. The only equation I know for calculating work is equal to negative P times delta V. So it says we have a constant pressure, external pressure of 15 atmospheres. So let's plug that number in here. So work is equal to 15 atmospheres. That's negative 15 atmospheres times a delta V. Well, delta V is 64. This is the final conditions, VF minus VI, and the VI is 46 liters, and the answer is 18 liters. So times 18 liters gives me negative 270 liters atmospheres. Now this is a different way to express work, and we're going to deal with this a little bit later, but it's just a different way to do it. So that is one quick calculation for calculating for work. Okay, here's another example, and you can do B and C or just like what we just did, but I want to talk about A. If I have a sample of nitrogen gas expands in volume from 1.6 liters to 5.4 liters at constant temperature, calculate the work done in joules if the gas expands. And of course, if I have an expansion of gas, I'll have negative work. Work is being done by the system on the surroundings, so work has to be leaving. So volume, I have to have a positive delta V. And that's what gases do. They expand or they compress. In this case, this particular gas says it is expanding. So if I'm going to expand a gas against a vacuum, it doesn't give me any numbers to solve this, but if I have a vacuum, it means I have nothing inside there. If I have nothing inside the vacuum, then I cannot be having any type of pressure whatsoever. So if I have 0 atmospheres of pressure times, what's 5.4? I'm just calculating delta V here, minus 1.6. That's 4, 14, 8. I have 3.8. 0 times 3.8 liters gives me 0 liters atmospheres. So work done on a vacuum or against a vacuum is 0. It's not doing any work at all. Sample exercise 6.3. Let's take a look at that one, and this will be the last one for this section. It says a balloon is being inflated to a full extent by heating the air inside it. In the final stages of this process, the volume of the balloon changes from 4.0 times 10 to the 6 liters to 4.5 times 10 to the 6 liters by the addition of 1.3 times 10 to the 8th joules of energy as heat. Assuming that the balloon expands against a constant pressure of 1 atmosphere, calculate the delta E for this process. Then it says to convert between liters, atmospheres, and joules. You're going to use this conversion here. Okay, so what I'm going to do is this. The question says, assuming the balloon expands against a constant, calculate delta E. Delta E is equal to Q plus W. All right, the problem automatically gives me the Q as being 1.3 times 10 to the 8th. So that's 1.3 times 10 to the 8th joules plus, but it doesn't give me a work, so I got to calculate for work. Of course, we just learned that work is equal to negative, whoopsie, let me change that, negative P times delta V. All right, so my negative pressure, in this case, the pressure is allowed to expand against a constant pressure of 1.0 atmospheres times delta V. Delta V is 4.5 times 10 to the 6 minus 4.0 times 10 to the 6th. That gives me an answer of 5.0 times 10 to the 5th liters. So when I multiply these, of course, that's a negative. So when I multiply these two together, I get negative 5.0 times 10 to the 5th liters atmospheres. Okay? But liters atmospheres doesn't match joules, or else I'd plug this number right into here. But since it doesn't match, I got to do something with that, and that is going to be a conversion. So that last little sentence in parentheses says that 1 liter atmospheres is equal to 101.3 joules. So when I multiply those two things together, I end up getting, let me see here, 5.1 times 10 to the 7th joules. 5.1 times 10 to the 7th joules. This number will plug in right here. So 5.1 times 10 to the 7th joules. And by the time I add, oops, that's a negative. Excuse me, that's a negative. And by the time I get these, let me change that for you guys. Negative. Okay, by the time that I add these two things together, I end up getting 8 times 10 to the 7th joules. 8 or 7.9 times 10 to the 7th joules. Okay, that's the first section. Again, if you have any questions or comments, come see me, and I'll see you guys tomorrow or mañana, whatever.